So we've got our capacitor. But you know what? Physicists like to mess with things. What can we do with our capacitor? Well, we could slide a dielectric material between the plates. Or we could remove the dielectric if it's already there. Maybe we can mess with the spacing between the plates. We can pull the plates farther apart or push them closer together. So let's take a look at one of those effects and see how it affects the voltage difference, the charge, the capacitance, and the electric field. I have here a charged capacitor that has been disconnected from the battery that charged it. And I'm going to take those plates and push them closer together. So originally they were a distance capital D apart, and I'm going to push those plates closer together so they're a distance lowercase d apart, a smaller distance between the plates. And we're going to see how all the properties of our capacitor change when we do that. We're going to fill in this table. I've filled in the first row for you. The spacing between the plates started out capital D. It ended up lowercase d. And that means it went down, it decreased. We made the spacing smaller. And we want to know, what about all these other things? The potential difference across the plates, the charge, the surface charge density, the electric field, the capacitance. How do all these other things change? Do they change? Let's see. Let's take a look at it. Maybe you should stop the video and think about it a little bit. See if you could fill in this table. The key here is understanding the order that things happened. This capacitor was hooked up to a battery and it charged up, and then it was removed from the battery. It is isolated. So there's no place for the charge to go. As we mess with it, the charge is fixed. It cannot change. There's no connections. There's no connection from one plate to the other. If it's hooked up to a battery, there's a connection from one plate to the other through the battery, and charges can move back and forth. The battery will move the charges back and forth to keep the potential difference fixed, because that's what a battery wants to do. It wants to keep a fixed potential difference between its terminals. But if there's no battery, if these plates are just isolated from each other, there's no place for the charge to go. The charge is fixed. Right away, we can go to our row that has charge in it and fill that in. If we started with charge Q naught, we're going to end up with the same amount of charge because it can't go anywhere and we can't get any charge from anywhere. So it stays the same. Let's jump to surface charge density. We just said the charge didn't change. Did the area of our plate change? No, we just changed the spacing between the plates, but we didn't make the plates bigger or smaller. The area of the plates, the surface area of the plates, is the same. So if the charge is the same and the surface area of the plate is the same, then the charge density must be the same. If it started out at sigma naught, it's going to end up at sigma naught. Let's take a look at electric field. How do we calculate the electric field between the plates of a capacitor? Well, we view them as infinite plates, and we use Gauss's law. And what do we get? The electric field is sigma over epsilon naught. We just said sigma didn't change. So our electric field doesn't change. Let's take a look. What do you want to do next? How about potential difference between the plates? So we charge them up to a certain potential difference. Let's call it delta V naught. And we know that those two plates have an electric field between them. And they're separated by a distance d. So the potential difference has to equal the electric field between the plates multiplied by the distance between the plates. So what do you think happened to our potential difference? Is it the same? No, because the electric field is still the same, but the distance has changed. So our potential difference between the plates is different now. We're multiplying the same electric field by a smaller distance to figure out the delta V between the plates. So our potential difference decreased. It got smaller. How about the capacitance? What does the capacitance depend on? It depends on the physical properties of the capacitor, the size of the plates, the spacing between the plates, and whether there's a dielectric in there or not, right? Those are the main things. And we messed with the spacing between the plates, so we changed the capacitance, didn't we? So our capacitance increased, didn't it? We could store the same charge on this capacitor that with the smaller distance between the plates as we could with the bigger one, but with a smaller delta V. A smaller battery would produce the same charge, so it must have a larger capacitance. Let's do it again, but this time we'll leave the battery connected. We're going to take a capacitor that's connected to a battery and has spacing capital D, large distance between the plates, and leave it connected to the battery while we push those plates together to make the spacing smaller between the plates. And it'll be connected to the battery the entire time. Let's see what happens in this case. Let's start with potential difference. If it's connected to a battery, the battery's job is to maintain a fixed potential difference across its terminals. It moves charges around until the potential difference on the plates of our capacitor matches the terminals of the battery. If we move the plates, the battery will just move charges around until it gets the right potential difference. So in this case, the potential difference is a constant. That's fixed because our plates are connected to a battery, a constant potential source. Let's think about capacitance next. Capacitance is epsilon naught A over D, and the distance got smaller, so the capacitance increased, just like last time. And we know that Q is equal to CV. C increased, delta V stayed the same, so that means the charge had to go up. More charge. The battery doesn't have to do as much work moving the charges because it's not moving them through as big a distance from one plate to the other. Let's think about our surface charge density. We just said the charge on our plates went up, but the area of the plates didn't change. We only changed the spacing between them. So our surface charge density must increase also. And that means that what happened to our electric field? It increased also, because the electric field depends on surface charge density. So there's a lot of things we can do with the capacitor. We can put the plates closer together, pull them farther apart, insert a dielectric, remove a dielectric, a number of things. But the key is it connected to the battery while you're doing this? Or is it isolated? Is it disconnected from the battery?